Hello friends, welcome to the tutorial series on network analysis made simple. In this tutorial, we shall solve the questions on network solutions from IES examination. Friends, we are required to find the value of current I in a pure resistance of 1 ohm in the circuit shown in figure. The problem is very simple if you know certain basic concepts. Number one, if the ideal voltage source and the ideal current source are in parallel, the current source will be redundant as shown in figure. The entire source combination will be equivalent to the voltage source. Similarly, if the ideal voltage source and the current source are in series in a branch of a network, the voltage source will be redundant as shown in figure. In view of these concepts, observe the given network. Since the current source is redundant, the voltage source of 5 volts will appear across 1 ohm resistance. So, current I is equal to 5 volts divided by 1 ohm equal to 5 amperes. Hence, option C is the correct answer. Friends, in this problem, it is given that a current waveform shown in figure is flowing through a pure resistance of 10 ohm. We are required to find the power absorbed in the resistance during the first period of 0 to 3 seconds. Observe the current waveform. It has a period of 3 seconds and it is a ramp function during that period. The slope of the function is 9 divided by 3 equal to 3. So, I of t is equal to 3t for t between 0 to 3 seconds. We know IRMS is equal to square root of 1 upon t into integration 0 to t I squared t dt, and IRMS squared is equal to 1 upon t into integration 0 to t I squared t dt. By substituting the values and solving, we get IRMS squared is equal to 27 amperes. But the power absorbed in the resistance of 10 ohm P is equal to IRMS squared into 10. And by substituting the values and solving, we get P is equal to 270 watts. Hence, option D is the correct answer. Friends, in this problem, we are required to find the voltage Vx in the circuit shown in figure. Observe the network. We find that there are 3 junction nodes, and let 3 junction nodes be designated as X, Y and Z as shown in figure. And let junction node Z be the reference node. The other junction node voltages Vx and Vy are to be found out. But observe that with reference to junction node Z, the node voltage Vy is known and is equal to -4. So, only one unknown junction node voltage Vx is to be found out. So, by writing the nodal equation for junction node Vx, we get Vx divided by 1 plus Vx minus 6 divided by 1 plus 2Vx plus Vx plus 4 divided by 2 is equal to 0. Note, 5 volts voltage source is in series with the current source of 2Vx amperes. So, 5 volt voltage source is redundant and it does not contribute any current in the branch. This is very important and you should remember this concept. By solving the simple equation, we get Vx is equal to 8 divided by 9 volts. Hence, option B is the correct answer. Friends, this problem is very simple. We are required to find the value of resistance R in the circuit shown in figure. The problem can be solved by different methods, but I prefer to solve using branch current method. Observe the given network. It is given that the current through R is 4 amperes. Let I be the current delivered by the source of 50 volts as shown in figure. By applying the Kirchhoff's current law to junction node A, we get the current in 7 ohm resistance will be equal to I minus 4 amperes. By writing the KVL for the loop 1, we get 50 minus 6I minus 7 into I minus 4 is equal to 0. By solving this simple equation, we get I is equal to 6 amperes. By applying KCL to junction node A, we get current through 7 ohm is equal to 2 amperes. Now, we see that 7 ohm and R ohm are in parallel. Hence, voltage across R will be 7 into 2 equal to 14 volts. Therefore, 4R is equal to 14. So, R is equal to 3.5 ohm. Hence, option A is the correct answer. Friends, observe the given network. It has a current controlled current source and we are required to find the ratio of V2 to V1. By applying the KCL for junction node V2 shown in figure, we get current through R ohm is I plus alpha I amperes. Also, observe that the current controlled current source and resistance R are in parallel and voltage V2 is across both the resistance R and alpha I current source as shown. So, V2 is equal to R into bracket I plus alpha I volts. But by writing the KVL for loop 1, we get V1 minus IR minus V2 is equal to 0. From which we get V1 is equal to IR plus V2. By substituting for V2 and solving, we get V1 is equal to IR into bracket 2 plus alpha volts. By taking the ratio of V2 is to V1, we get V2 is to V1 is equal to 1 plus alpha divided by 2 plus alpha. Hence, option B is the correct answer. Friends, in this problem, a resistor network connected across a voltage source of 6 volts is given. We are required to find current I delivered by the voltage source. Fine. To solve this problem, if you are thinking of applying mesh analysis, you find that there are 5 independent loops. So, mesh analysis is not a good selection. If you think of nodal analysis, the circuit contains 5 junction nodes. So, nodal analysis also is not a good selection. Hence, this network should be solved by reduction process. But when you select the reduction method, do not jump immediately to identify star and delta connected elements and start reducing the network. If you do so, you will end up into more complications compared to mesh and nodal analysis. Then, what is the way out? Friends, you must think out of the box and arrive at the easiest solution process. So, observe that the terminals to which 2 ohm, 3 ohm and 6 ohm at both the ends can be used to redraw the network as shown in figure 2. Friends, observe that the network is redrawn retaining the same connectivity. Now, I hope you can recognize a feed stone bridge with two arms of the bridge with 2 ohm each and another two arms with 3 ohm each. The central branch is of 2 ohm. Examine this bridge if it is balanced. If balanced, the current through the central branch will be 0. So, let I1 be the current in 2 ohm branch and I2 be the current in 3 ohm branch. Then you find that 2I1 is equal to 3I2 from both ends of the terminals. Hence, you find that the bridge is balanced. So, current through the central branch of 2 ohm is 0. Hence, it can be considered as open. Similarly, the other bridge consisting of 3 ohm branch and 6 ohm branch also is balanced. Hence, central 3 ohm branch can be considered as open. Friends, now we see that the series connected resistances 2 ohm plus 2 ohm is equal to 4 ohm, 3 ohm plus 3 ohm is equal to 6 ohm, and 6 ohm plus 6 ohm is equal to 12 ohm. By incorporating these values, the circuit drawn is shown in figure 3. Now, you find that 4 ohm, 6 ohm and 12 ohm are in parallel and their equivalent is 2 ohm as shown in figure 4. So, current I is equal to 6 volts divided by 2 ohm equal to 3 amperes. Hence, option C is the correct answer. Friends, this is the simple and straightforward question. We are required to find current I in the AC circuit shown in figure. Observe the given network. We find that the voltage V of t is equal to 120 sin omega t is applied across the parallel combination of 60 plus j60 and minus j120 ohm impedances. If we find Z equivalent, we can straight away find I. Hence, we know Z equivalent is equal to Z1 into Z2 divided by Z1 plus Z2. By substituting the values and solving, we get Z equivalent is equal to 120 plus J0. But I is equal to Vm divided by Z equivalent. By substituting the values and solving, we get I is equal to 1 plus J0 amperes. Hence, option B is the correct answer. Friends, in this tutorial, we have solved few interesting IES examination questions. During the next tutorial, we shall meet and solve some more interesting problems. Hope this presentation has kindled some of your thoughts. Thank you for watching.